Hey everyone, I'm Nguyen-Tu, and this is Lab 3 of Physics 2211. This lab is split into two parts. The purpose of the first part is to analyze a star's motion to find the mass of a black hole whose gravitational force is assumed to be the only force acting on the star. The purpose of the second part of this lab is to determine the initial velocity a spaceship will need to go around the black hole from part 1 without crashing, relying on the gravitational forces of the black hole and a planet orbiting the black hole on the spaceship. In this lab, I will be using Newton's second law and the momentum principle. Newton's second law is force equals mass times acceleration that tells us the acceleration of an object is directly related to how much force is applied to the object. The momentum principle tells us that in an isolated system, momentum is conserved for any interaction between two objects. Incorporating these two physics principles in my model with the velocity update formula, obtained by dividing both sides of the momentum formula by the mass of the object, I can predict the motion of my chosen object over time. Also in this lab, I'll be using the component breakdown of dp/dt, in which dp/dt is broken down into its parallel component that covers the change in magnitude of momentum speeding up or slowing down, and its perpendicular component that covers the change in direction of momentum and points toward the center of the kissing circle. This lab also involves the theory of gravity that states the force of attraction between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them, and Newton's third law, or reciprocity, that states for every action there is an equal and opposite reaction. To complete this lab, I'll be following 5 steps. First, I'll edit the given part 1 starter code with an email-based unique seed. Second, with code, I'll calculate the star's motion to find the net force acting on the star over time. Third, I'll approximate the black hole's mass with the dataset collected from step 2. Fourth, I'll input the approximated black hole's mass into the part 2 starter code. Fifth, through trial and error, I'll figure out the initial velocity of the spaceship such that it can go around the black hole and leave the black hole system without crashing. In part 1, the main result is that the black hole's mass was approximated to equal 1.4366 times 10 to the 34th kilograms. In part 2, the main result is that the spaceship's initial velocity through trial and error was found to be 3.70873 times 10 to the 7th meters per second in order to get close to the black hole center and escape from the black hole system without crashing. This closest distance to the black hole center was 2.02853 times 10 to the 8th meters. Shown here is the part 1 model. The system is the star and the surroundings is the black hole. The star initial conditions is mass equal to 2.0 times 10 to the 30th kilograms, the velocity is determined, and time is set to 0 seconds. Shown here is the part 2 model. The system is the spaceship and the surroundings is the black hole and the planet. The spaceship initial conditions is its mass of 7 times 10 to the 10th kilograms and its velocity at negative 3.94526 times 10 to the 7th meters per second in the x direction and 1.7 times 10 to the 6th meters per second in the y direction. The start time is set to 0 seconds. The mass of the black hole was found through part 1 to be 1.4366 times 10 to the 34th kilograms, and the mass of the planet was given to be 9 times 10 to the 28th kilograms. In part 1 of this lab, the assumption is that the only force acting on the star is that of the gravitational force of the black hole. In part 2, the assumption is that the only forces acting on the spaceship are the gravitational forces of the black hole and the planet. Shown here is the GlowScript VPython code for part 1 of this lab. On the left, boxed in their respective color, is the code that determines the colors of the items listed in the model key. On the right is the code for the initial conditions mentioned earlier. Of note, the calculated x component and y component of the velocities from the data are respectively stored in the xvel and yvel variables. Shown here is the calculation loop for part 1 in which the x and y velocity components stored earlier are combined to reconstruct the velocity of the star at each data value. From there, the net force acting on the star is calculated with the physics fundamental principles and definitions. Of note, the mass of the black hole is approximated by summing all of the black hole mass calculations from the data values and then dividing it by the number of data values. The code for this step of the calculations is boxed in black. Here is the GlowScript VPython code for part 2 of this lab. Similar to part 1, I have on the left box in the respective color the code that determines the colors of the items listed in the model key. On the right is the initial conditions of the model mentioned earlier in code. Of note, at the bottom right, the values for ship speed were found through trial and error. This section of part 2's code is the calculation loop. It calculates the net forces acting on the planet and the spaceship with the relative position vectors and the gravitational force formula. With the calculated net forces, the velocity update formula, and the position update formula, the loop updates the planets and ships' positions in the model. Of note, the closest the spaceship gets to the black hole is stored in the lowest RBH2SH variable. The code for this is boxed in orange. In this lab, there are sources of error. In part 1, it was assumed that the only force acting on the star is the gravitational force of the black hole on the star. That being said, we know from part 2 that there is also a planet and spaceship in the black hole's orbit that could have an effect on the star. In part 2, it was assumed that the only forces acting on the spaceship is that of the planet and the black hole. However, we also know from part 1 that there is a star orbiting the black hole that could have an effect on the spaceship. Now for the discussion part of this lab. How is the net force and its parallel and perpendicular components different from the rate of change of momentum in its parallel and perpendicular components? The net force is the sum of the interactions between the system and its surroundings, while the rate of change of momentum is how fast the object's speed changes over a period of time. Therefore, they are different because the rate of change of momentum can be directly measured from the observations over time, while the net force cannot. In part 1 of the lab, I was able to observe the motion of the star and calculate the velocity and then momentum from the data values collected through the definitions of velocity and momentum. From the change in momentum over time and the momentum principle, I was able to find the net force at each point in time. I was not able to directly calculate the net force from the observations. What initial velocity would allow the spaceship to orbit the black hole without crashing? One initial velocity that worked according to my part 2 model is an x-component velocity of -3 times 10 to the 6 meters per second and a y-component velocity equal to the planet's initial speed. The resulting orbit of the spaceship is seen in magenta while the cyan orbit is that of the planet.